Hello everyone. In this module, I will talk about infrared spectroscopy. Now, infrared spectroscopy, that is called IR, and Raman spectroscopy, are two types of vibrational spectroscopy, and they are concerned with transition between vibrational energy level. Here you can see that this is an energy level diagram. Different energy level is shown over here. The rotational energy level, vibrational energy level, and electronic energy level. Now, vibration energy level, you can see that this designation V0, V1, and this is the vibration energy level for ground electronic state, and V0, V1, this is the vibration energy level of higher fast excited state, electronic state. This E0, this E1, this E1, E2, these are electronic excited electronic state. So for a particular electronic energy level, there are rotational energy level, and you can see there are vibrational energy level. Now this transition, this A, B, C, these are called transition. Now if you can see that this transition A, it is purely rotational transition. Now this transition B, it is rotational plus vibrational transition. Now you can see the transition C, it changes the electronic energy level. So it is basically electronic transition with changing the vibrational energy level also. So now for IR spectroscopy, it is purely vibrational transition. Like this transition occurs between the two vibrational energy level for V0, V1, like this. Now coming to the energies and wave number of molecular vibration. When a molecule absorbs IR radiation, it undergoes vibrational motion. Stretching of a covalent bond is like stretching a spring, and molecule undergo enharmonic oscillation. Now vibration energies are quantized, and these energies are given by this equation EV is equal to V plus 1 by 2 h nu minus V plus 1 by 2 whole square h nu xc, where this V is the vibrational quantum number, h Planck constant, nu is the vibrational frequency, and xc is the enharmonic constant, enharmonicity constant. For a case if as it is usual the case, we are concerned only with the transition from vibrational energy level from ground state to fast excited state. Then if you put V is equal to 0 and then V is equal to 1, you for these two energy level, ground state to fast excited state, you will the equation will reduce to this equation EV is equal to V plus half h nu. Thereby, this enharmonic oscillator equation reduced to simple harmonic oscillator equation. Now consider a diatomic molecule XY, for example. Now this vibrational frequency of this diatomic molecule depends upon the bond strength, and it is designated as a parameter force constant capital K of the bond. Now the force constant is a property of that bond of the diatomic molecule of any molecule and is related to its strength. If we return to the stretching of a spring, then the force constant is measure of the stiffness of the spring. So basically the value of force constant gives the idea how the strong is that bond. If the atom X and Y are similar masses, they contribute almost equally to the molecular vibration. However, if the masses of the two elements are different, then the lighter atom moves much more faster than the heavier one. It is therefore necessary to define a quantity that describes the mass of a oscillator in a way that reflects the relative mass of that two atoms X and Y. Therefore, that and then for that reduced mass concept is comes into picture, and it is given by this mu, and reduced mass is given by 1 by mu is equal to 1 by mx plus 1 by my. But mx my is the mass of this two element for a diatomic molecule X and Y, mass of one element X and mass of the another element Y, and this mu is represented as this form 1 by mu is equal to 1 by mx plus 1 by my, and you can rewrite this equation mu is equal to mx into my divided by mx plus my. This mu is a reduced mass. Now for a diatomic molecule, the transition from the vibration energy level from ground state V is equal to 0 to V is equal to 1 fast excited state gives rise a fundamental transition absorption band. Now this equation, if you derived using this value v is equal to 0 to v is equal to 1 transition, this is equation fundamental frequency nu comes. Nu is equal to 1 by 2 pi root over k by mu. The k is the force constant and this mu is the reduced mass and nu is the fundamental vibrational frequency. So if you rewrite this frequency into the wave number form, you divided uh, you divided the you divided the speed of the light with 1 by 2 pi c, then the nu bar will be 1 by 2 pi c root over k by mu basically. So basically the relation is that nu bar is equal to 1 by lambda. Nu bar is equal to 1 by lambda, and you know that the relation between this frequency and wave, speed of the light. So one can easily change this frequency form, which is in the hertz, can be converted to the centimeter inverse or meter inverse in the wave number form. So basically, so then nu bar is equal to 1 by 2 pi c into root over k by mu. So this term will be in the centimeter inverse or meter inverse depending on the value of c. Now the Hooke's law, nu bar is equal to 1 by 2 pi c into root over k by mu, that I have already talked about the last slide. So this is the vibrational frequency. From that one can calculate the vibrational frequency of a particular molecule in different vibrational frequency. Now this nu bar is represented in centimeter inverse. K is force constant, which measures the bond stiffness, and mu is the reduced mass. Now what are the significance of this equation? Now the position. Now how the position will get varied of the nu bar. The first one is reduced mass. The reduced mass actually play a role by the for the position of this frequency. Bond strength, that is key. Bond strength is an important factor in order to get the position of a value of that vibrational frequency. For example, light atoms, they are having high frequency. Strong bond are having high frequency. Now the strength of this frequency, I mean in the intensity of that particular vibration, is related to the change in the polarity of the molecule, that I have already talked in the last part, that change in the dipole moment is very important in order to observe the transition of IR transition. Now the strong polar bond give intense band. If a bond is much polar, it will vibrate and it will change its dipole moment and it will give a strong intense band. Now the width of band. Now for IR, the width of the band depends on different factor. One of the factor is the hydrogen bonding. If the molecule forms strong hydrogen bonding, it gives a very broad band in the IR region. I will come into the part later and show you some example. Now, what are the consequences of this Hooke's law? There are simple chart I have prepared where you can see that carbon carbon single bond to carbon carbon double bond, carbon carbon triple bond, or moving single to triple bond, the bond strength of carbon carbon single bond double bond triple bond getting increased, which is quite obvious, and thereby the its frequency is also getting increased. You can see that 1200 centimeter inverse to 1650 centimeter inverse to 2150 centimeter inverse. It is because of that increasing K. The here the mu is same because two atom is carbon same. The factor which actually changing their frequency value is that bond strength. So when you increase the bond strength, it means increasing the K value, the vibrational frequency or wave number value getting the value will increase, as you can see over here. Similarly, if you see that carbon hydrogen stretching frequency, 2930 centimeter inverse for sp3 carbon. For sp2 carbon, the CH stretching frequency is much higher. For sp carbon, CH stretching frequency is much higher also. This is also the same trend, the bond strength. Here the carbon hydrogen stretching frequency in case of sp3 case, the bond strength frequency is lesser than that sp2 carbon CH, which is also lesser than that of sp carbon CH bond strength. Here you can see that by changing the atom hydrogen to carbon, oxygen, chlorine, bromine, iodine, the bond strength, the frequency or wave number value, actually you can see that it getting gradually decrease from 3000 centimeter inverse to 500 centimeter inverse. And this is because of the fact that for the two atom here, CH, COC, CL, Br, Ci, the carbon is fixed. When you increase the mass of that second atom from hydrogen to carbon to oxygen, chlorine, bromine, iodine, the reduced mass getting increased. The reduced mass, you know all that, mu is equal to m1 m2 divided by m1 plus m2. So when you increase the reduced mass of that atom, automatically the nu bar is proportional, inversely proportional 1 by root over mu. So the frequency or the wave number will gradually decrease. As you can see that 3000 centimeter inverse to 500 centimeter inverse. This is because of the fact that increasing mass, increasing reduced mass, increasing mu, the frequency or wave number getting decreased as in this series. Now coming to Fourier transform in infrared FTIR spectrometer and sample preparation. So this is the picture I put. It is for Fourier transform FTIR spectrometer in a forensic crime laboratory. Now the IR region is from 20 centimeter inverse, far IR to 1400 centimeter inverse, near IR. But most laboratory the IR spectrometers probe only in the mid IR region, that is 400 to 4000 centimeter inverse. So in addition, in the analytical tool in the laboratory, IR spectroscopy has application in the field of forensic sciences and astronomy. Now the output data may be collected in the form of, I have shown over here, transmitted versus wave number or absorption versus wave number. You can see that this is an IR spectrum which can be recorded in terms of transmitted or absorbance and provide information about the energy and intensity of the absorption. Here you can see that this transmitted versus absorbance wave number plot. So this, here you can see that the for this peak actually 0% it is transmittance, means it is 100%, it absorbs 100% of that IR light, infrared light. That is why in this diagram, absorption versus wave number plot, you see that that peak actually is 100%, that is 100% absorbance. So 100% absorbance means 0% transmittance. So infrared spectra can be recorded using gaseous, liquid or solid sample. Spectra of gases usually exhibit rotational structure in addition to the band arising from the vibrational mode, whereas solid sample have traditionally been prepared in the form of mull in organic oil, example nozzle, or as a pressed disc in which the sample is grounded with an alkali metal halide, for example KBr pellet. Here I will discuss some of the diagnostic absorption. Uh, IR spectra of inorganic and organic compounds can generally be separated in two regions. Absorption above 1500 1500 centimeter inverse can typically be assigned to a specific group, functional group, while the band below 1500 centimeter inverse tend to arise from a single bond stretching mode, deformation and vibrational modes of molecular framework. Now this latter region, that actually below 1500 centimeter inverse region, is called the fingerprint region, and the absorption within this region are usually taken together to provide a diagnostic signature of a molecule. So this is some typical ranges of fundamental stretching wave number and selected group. You can see that OH having a stretching frequency 3500 to 3700 centimeter inverse. If OH is hydrogen bonded, then this value actually getting reduced 300 to 3500 centimeter inverse. Similar for NH also 3200 to 3500. This OH NH actually falls in the pretty close similar region. So it is difficult to find out the OH and NH difference between this OH and NH stretching frequency. So there are several factors I will talk about later. Now the CH stretching normally comes in this region 2850 to 3000. It include all this CH of this sp3CH, sp2CH, spCH of this kind of uh, state. Similarly, this you can see the inorganic boron hydrogen breached value comes in this region 2100 to 1600 centimeter inverse. The important part is that this carbonyl CO organic, that is carbonyl stretching. So it comes in this region 1650 to 1750 centimeter inverse, this region. When you change the oxygen to nitrogen, the C11N, the organic moiety, you see that the value actually falls from changing oxygen to nitrogen 1630 to 1690 centimeter inverse. This is also related to the polarity of the polarity or dipole moment change. When you change the more electronegative oxygen to less electron nitrogen, you will see that thing happening. Although the now you see that carbon monoxide ligand, this is ligand, not that CO of organic. This is carbon monoxide ligand. Terminal MCO, where M is the metal atom. Then the value falls in this region 1900 to 2200 centimeter inverse. If this carbon monoxide CO ligand is bridging between two metal, then its value is actually getting reduced that of terminal 1700 to 1900 centimeter inverse. Similarly for NO, you can see there is two form, one is linear and one is bent, binding to metal. Linear has a higher wave number 1650 to 1900, whereas bent has a lesser wave number 1525 to 1690 centimeter inverse. So this chart actually pretty informative regarding the different fundamental stretching vibration of selected groups. Now, how to calculate the vibrational degree of freedom? There are two formula for linear molecule. It is 3n minus 5. N is the number of atom. So this 3n minus 5 is the 3n minus 5 degree of freedom of vibrational mode. For non-linear molecule, it is 3n minus 6 degree of freedom. Like this number of vibrational one molecule can have in case of linear and non-linear. Let's take an example, two examples. This water molecule, we all know that it is bent, not linear in shape. So if we apply the formula 3n minus 6 here, so NH is equal to 3 because there is 3 atom, 1 oxygen, 2 hydrogen. So 3 into 3 is 9 minus 6. You will get 3 degree of freedom, means 3 vibrational degrees of freedom is the water molecule is having. Now 3 of these vibrational mode is shown over here. One of the is antisymmetric stretch. You can see that one of the oxygen hydrogen bond is stretched and another oxygen hydrogen bond is stretched much higher than that of other. Symmetric stretch, where two of these OH bonds are stretched in the equal extent. And this third part is that bending. One of the bending is this scissoring bending. So water molecule has these three kind of vibrational degree of freedom, vibrational mode, and all these modes are IR active. Not necessarily these 3n minus 5 or 3 minus 6 degrees of freedom. All these degrees of freedom have to be IR active. Only those degrees of freedom which associated with change in the dipole moment, that particular vibrational degrees of freedom will be IR active. Not all the degrees of freedom will be IR active. Similar, carbon dioxide, you can see that it is a linear molecule. Now for you apply this formula 3n minus 5, 3 into 3, 9 minus 5, so you will get 4 degrees of freedom. Now the 4 stretching frequency is shown over here. Now this, for the symmetrical stretching of carbon dioxide, this particular mode is IR active, because in this mode, symmetrical stretching mode, there will be no dipole moment change, because you are extending this CO bond with the both side with equal extent. So overall dipole moment will cancel each other. From one side, it will cancel the other side. Antisymmetric stretch, it is IR active. Now these two modes is the bending mode of this carbon dioxide molecule, and it is degenerate same energy. So you will understand that how to calculate the degrees of freedom, and not necessarily all degrees of freedom have to be IR active. Only those will be IR active that are associated with changing the dipole moment. Here I have shown that IR analysis of human breath. You can see over here at the point I am showing the pointer. This is for that carbon dioxide bending mode, and this intense band is for carbon dioxide antisymmetrical stretching mode that I have talked in the previous slide, which is IR active, which is associated with change in the dipole moment. And other two, this small intense band, it is for water molecule bending and stretching mode. You can see that this antisymmetrical stretch and this is this bending mode. So this is one of the example of IR spectrum, and by carefully looking into it, you will understand this carbon dioxide stretching bending mode and water molecule stretching bending mode that is most probably we have in our breath. Now let's do some example in order to understand the IR spectrum of different organic molecule. So this range I have already talked, this 500 to 1000 centimeter inverse is called the fingerprint region, which is normally not useful. Uh, so this part you will see that 1650 to 1800 centimeter inverse. This is for carbonyl stretching frequency, carbonyl stretching frequency, not the carbon monoxide ligand which is bound to metal. So this region is very much important, and this region normally gives very intense band. The reason is that change in the polarity is higher compared to uh, other functional group, like this carbon carbon triple bond, carbon nitrogen triple bond. You will see that band intensity is much lesser than that CO stretching frequency. Because of the same reason, the extent of change in dipole moment is lesser here. Because of the same element like carbon carbon, there is no change in, there is very less change in polarity, because their electronegativity difference is less for carbon carbon and carbon nitrogen also, whereas this carbon oxygen, the change in electronegativity difference is high, therefore it gives the intense band because of the high polarity change during its vibrational mode. And this region, the 3100 to 2850, it is for CH stretching frequency. For alkyl CH stretch, it is normally lesser than 3000. For sp2 or sp like alkyl, it is greater than 3000 centimeter inverse. Now important part is that OH, which is shown in the blue in color, it falls in this 3000 to 3200 to 3400 region. This broad band, it will normally gives a broad band, and depending on the hydrogen bonding, the broadness will increase. The NH stretching frequency also fall in the similar region shown over here, this region. So this is pretty informative, this chart, in order to find the analyze the IR spectrum of different unknown inorganic organic molecule. Now two representative examples I have shown over here. This is the ethanol molecule, where you will find the interesting band over here. This broad band around 3300 centimeter inverse. It is for that OH, ethanolic OH group functional group. I have already talked about the OH functional group position, and it broad, and this band is very broad in nature, and it is due to the fact that this ethanol molecule is hydrogen bonded with each other, and also with some water molecule also. And this band around 2961 centimeter, it is for this sp3ch stretching frequency. Similarly, there are another band around 1055. It is for this carbon oxygen single bond stretching frequency. Let's take this another example. This is an secondary amine, where you can see that this NH stretching frequency, which is closer in energy that are OH stretching frequency falls in this region 3 to 6 centimeter inverse. This is NH stretching frequency. This is for the secondary amine, and this splitted band it is for that sp3ch, or you can say there are different degrees of one is ch3 ch2 ch3 ch2. So this band actually is from this CH stretching of this molecule. Carbon nitrogen stretching frequency is similar to that of carbon oxygen stretching frequency. You can compare it there. This falls in 1 on 40 centimeter inverse. Now this NH stretching frequency, I have already talked this value 3 to 6 centimeter inverse, but there is another part which is this 733 centimeter inverse. This is NH actually bending mode, wagging. This NH wagging. This is one of the bending mode of this NH, and this is a stretching. Always remember that stretching frequency higher in energy and bending mode requires lower energy. So always stretching mode will falls in the higher energy region, higher wave number region compared to that of bending mode. So here I have shown the IR spectrum of inorganic salt, uh, which I will discuss right now. So the inorganic anion, sulfate, nitrate, all these inorganic anion, when it is free state, not bound to metal, it has a particular wave number, vibrational energy, vibrational mode. But when bound to metal, due to binding with metal, it changes its vibrational frequency. And also depending on upon the binding nature, this frequency will also varies. Like you can see that this sulfate SO4 minus 2, the charge is not shown over here for simplicity. When it binds to the oxygen atom, it can also bind with this bidentate fashion. Also, this sulfate anion can bind the two metal center in a eta1 eta1 fashion also. So depending on the nature of binding, the value of this vibrational mode of this inorganic anion will also vary. Here I have shown this cobalt hexaamine salt, where sulfate is a counter anion. SO4 is a counter anion. The IR spectrum is shown over this red color spectrum. You will see that the very broad band around this 1000 to 1 to 222 centimeter inverse, it is called the sulfate anion stretching frequency. This very broad band, and this is because of this that this sulfate anion, this sulfate when it is in free state or when it is in counter anion, not bind to the metal, it has a symmetry, and because of its symmetry, it gives this kind of broadband. But however, when this in the second example, this pentamine cobalt sulfate salt, where sulfate is bound to the cobalt center, where the bromine is counter anion, you can see that the spectrum shown over green, there are splitting in that region. So this is because their sulfate is binding with the one of this atom oxygen to the metal center, and because of binding, the value, the pattern will getting changed, and you will get that fine splitting structure in the IR spectrum. The symmetry actually normally getting reduced, getting lost when this sulfate anion or any inorganic anion binds to the metal center, and that is why initially it gives a very broad band which is symmetric in nature, and when it binds to the metal center, the symmetry is lost, and it gives this splitting, this kind of band structure. Deuterium and hydrogen exchange. When the hydrogen atom in an XH bond is exchanged by deuterium, the reduced mass of the pair of bonded atom changes and shifts the position of the absorption in the IR spectrum due to the XH stretching mode. Shifts of this kind can be used to confirm the assignment in the IR spectrum. For example, NH-OH CH bond all absorbs around this 3000 to 3600 centimeter inverse. However, if a compound contains both CH, NH and OH bond, it is difficult to analyze this kind of spectrum. So in that case, if you say that compound with D2O, usually only NH and OH groups undergo rapid deuterium exchange reaction. As shown over here, this D2O reacts with ROH or RNH rapidly to give that ROD and HOD. And therefore, the position of that band, OH band, NH band, will shift it to lower number, lower frequency. Because of the deuterium is heavier than OH hydrogen, because of that reduced mass is getting increased, and so therefore this new bar will also decreases. So an hydrogen atom attached to it directly to carbon exchange extremely slowly, except in case where it is acidic. So because therefore, so one can distinguish between the CH and OH or NH bond. Because CH bond exchange is difficult, it will not happen, but OH NH bond can exchange with the D2. So by observing which higher spectroscopic band shifts and by how much, it is possible to confirm an assignment of an NH, OH and CH absorption. Now let's try out this what example. It is based on this deuterium exchange reaction. So this question says that an absorption at 3650 centimeter inverse in the higher spectrum of a compound X has been assigned for OH stretching mode. Now to what wave number is this band expected to shift upon deuteriation? So if you change this hydrogen to deuterium, like by the reaction with D2, so what will be the value of the wave number? Changed from 3650 centimeter inverse. What assumption have you made in this calculation? So in order to do this problem, we have to go to that Hooke's law equation, that mu bar is equal to 1 by 2 pi c root over into root over k by mu, where k is a bond constant, bond strength constant, and mu is a reduced mass. So the assumption here we will make that by changing OH to OD, the K value will remain same. The bond strength constant K will remain same. Therefore, you can calculate that reduced mass and you can compare with that stretching frequency. So therefore, this new OH, this frequency will be inversely proportional to root over reduced mass. So if K is constant, then the other parameter will automatically taken into account. Then if you divided these two part, nu bar OH, nu bar OD, so because of this inversely proportional equation, the nu bar OD divided by nu bar OH is equal to root over mu OH divided by root over mu OD. Now once you can calculate this mu OH and mu OD by knowing that oxygen has mass of 16 and hydrogen has a mass of 1.01. So you can calculate this mu OH reduced mass, mu OD reduced mass. Other than that, in short, if you see that here oxygen is in this bond OH and OD, the oxygen atom is fixed. You are changing this hydrogen to deuterium. So basically, you are changing 1 unit extra to deuterium. So because hydrogen has a atomic mass 1 and deuterium has 2, so in that sense, if you change the ratio, if you basically put here this nu bar OH, this is basically 1, and nu bar OD, this is basically 2. So therefore, if you have this value and if you multiply it with that nu bar OH, that is 3650 centimeter inverse, you will get that value close to this value, 2662 centimeter inverse. Otherwise, you can calculate in this way by calculating the reduced mass and then in this form multiply it with the OH fundamental frequency. And this tricks is that you are changing the hydrogen to deuterium. So because hydrogen has a mass of 1 and deuterium mass of 2, so if you put that in this form, so then you can easily calculate this value. Otherwise, if you do the similar thing also, if you divided this mu OH divided by mu OD, you will find closely to this value also.